VM Radio presenta.
En VM existe la libertad de cátedra. Los comentarios emitidos por el autor de esta presentación son responsabilidad exclusiva del mismo y no necesariamente representan el punto de vista de la universidad.
Hola, ¿qué tal? ¿Cómo están? Bienvenidos a esta nuestra conferencia magistral del día de hoy en el área de ingeniería. Es para mí un honor y un agrado el presentar y moderar esta sesión, aquí por supuesto en VM Campus Guadalajara Sur. Y bueno, voy a presentarles al doctor Holger Meinel. Holger, good morning.
Good morning, buenos días.
Buenos días, Holger. I will introduce you so the people who is looking online and is in our auditorium can know who you are. But only I want to say that you are an expert in automotive radar technology. Holger joined the AEG Telefunken Advanced Technology Department in Ulm, Germany. After he obtained his diploma in engineering from the RWTH Aachen in Aachen, Germany. As a research and development engineer, he designed components for 35 gigahertz anti-collision radar for cars. Following this, he was the supervisor of the radar subsystems and of the millimeter wave integration group, respectively responsible for development of hybrid technology for millimeter wave radar and communication systems with emphasis on commercial and scientific applications. Before he became manager of the RAF Systems Department in the radar division of AEG Telefunken, having been responsible for the development of ACM and radar systems up to the millimeter wave range. He recently obtained an IEEE award for their contributions for the development and promoting of the application of millimeter wave technology in transportation systems. Holger, we are excited to listen to you and hear more about all these technologies. You're welcome.
Okay. Thank you, Emanuele. Thank you for your kind introduction and even more for your invitation to give me the chance to talk here in your UVM presentation. All right, let's start. Give me the first picture and we go into it. All right, everybody. Okay, here you see it. I will try to talk about automotive radar technology and give you a little bit of the glimpse of what is happening there, the history, the state of the art that we have in the moment, as well as the future development directions to give you at least a glimpse what is happening and how interesting that can be for you young students and people who want to go into that field. The next one, please. Why me? That's very easy. If you see me here in the car, this picture is about 50 years old and it shows me. I was a young engineer at those days and just sitting in our first test car and with long black hair to the shoulders, a black bird and things like that. That has changed a little bit. I'm getting a little bit older now. Okay, why this special Ford Consul? That's easy to say. This is a car that you could buy with 4 different engines, 4, 6, and 8 cylinders. If you bought it with a 4-cylinder version, then you had a lot of room between the grille and the real engine of the car, and that we needed for our first 35 gigahertz radar. Next one. Yeah, here I want to talk a little bit about the contents of what I will try to bring over to you within the next 45 minutes. First of all, the motivation, the road traffic death toll. Then I talk about the history and the technological beginning of the whole story, automatic cruise control and blind spot detection, and I will focus a little bit on China because this is a new area that comes up. And today's state of the art will be the next stop. Commercial ongoing, the frequencies of today 24, 76 to 81 gigahertz, and the market, the key players. And then we will talk about what is the future and where you can come in, what is still all open and has to be developed to make it happen right. Next one, please. Here you see the traffic-related death rate, and that is not so new, but I didn't find anything newer than for the entire world. It's difficult to find. It's 2016, and we still had 1.35 million of fatalities due to road traffic. The worst is Africa. The least is Europe, and the United States, and your country is more or less the same. Brazil and South America isn't that good. It's a higher rate. So there's a lot of things that we can do to reduce that. And I hope I will bring that over while I talk. The next one, please. This is a view graph from Continental, one of the big players in the field, and I like it very much. You see that from 1954, where we had just, what was it, um, some thousands of cars in Germany, to 50 million in 2010, the amount of fatalities went down, which you see the seatbelt came, the ABS came, the airbag came, the electronic steering came, and ADAS came, and always the death rate went down again. There's only in the middle of this green curve you see ESC, which is very funny that it goes up. That was the moment of reunification in Germany when a lot of the people in the east of Germany got larger and faster cars, and that was when more accidents did happen. That gives you a little bit the overview where we are, and this vision zero, that nobody has to die on roads anymore, is becoming interesting again. As you see here on the right side, you see the European Microwave Week of this week. This is only 4 weeks over. There was a poster on Vision Zero combined with zero emission, because for an e-car, an electric vehicle, for an EV, you need also a radar for recuperation, for good recuperation, to reloading the batteries. So why you have two different setups in the same car where you don't have too much energy available because it's a battery driven car? Okay, so there's a lot of things to do to bring those two together. Next one, please. Here starts the early history. Our first 35 gigahertz car radar, which was built in 74. Distance warning radar, we called it, from Telefunken in those days. You see on the right side how big the antennas are, and that it was not so easy to bring them in the front of the cars. You see that down here, the Mercedes and some other Fords and so on. And you see that the whole thing is something like 70 centimeters broad and has to get into the front of the car. The next one. Here you see the block diagram. We started with two-pole devices. That means impact diodes, impact avalanche transit time. You put a voltage to a diode like that, and if there's a resonator, then it is at the right moment. This resonator is resonating, and you have pulses in this type at 35.6 gigahertz that are 10 to 20 nanoseconds long or wide. And for the receiver, we had a gun diode oscillator at 30 5.3 gigahertz with a Schottky diode mixer from GSC Hurst. In those days, that was the best that you could get in those days. It was developed for 18 gigahertz application, and I used it for 35 gigahertz. That was my own work at the beginning as a young engineer. And you see in this picture on the right, there's a little quartz substrate where there are these structures that have to be soldered orthogonal into the waveguide, and on that little substrate orthogonal in the waveguide, it's a soldered beam lead diode and contacted to the outside world with resonators being as a printed version microstrip on this quartz substrate. Quartz substrate is something like 110 microns thick, so it was not so easy to deal with the whole thing. The beam lead diode is 800 micrometers long, so that was the first work, and it worked. As you see, we had something like 3.5 dB conversion also with that mixer, and that was a quite robust mixer in the car. It could work on streets. Next slide, please. Here you see the first radars that were there. It started in 72 with RCA. We came in 74. Lucas Limited in England. Then there was SEL. You see the SEL on the right side of the picture with the big KU band radar in front of the car. And then you see HIT from Israel. You see VDO with a 10 gigahertz radar on the roof, and on the left side you see our BMW and also some other things from SEL and the Lucas radar. And something special just below the Professor Roland, who did something which is more an optical design of a radar, but that still worked and already took what we have now at 140 gigahertz or more happening. Next slide. From the very beginning, we were not directly only using something like sedans, but we had the radar being built in big trucks as well, because we had the feeling this is an important part to do that as well and come and helping the traffic on our roads. Okay, next slide. It goes on a little bit with the history of the others, Toyota, Nissan, and so on. And on the right side above, you see the solution of the Japanese. They were not sure if you get too many wrong reflections, and so they said transmission and receiving under 90 degrees to make it orthogonal, to make it easier to distinguish. However, what you can get back is so mixed with everything that in the end, this didn't help at all, and it is not necessary. You see TRW, you see Nissan, VW Rockwell, and what is good to see is the Toyota, the Fujitsu sensor, which went into the Toyota, which is a movable plate. On the left side above, you see DASA, the new name of Telefunken, then Deutsche Aerospace AG in Ulm, the same company, and you see the C model with three antennas as a system. By the way, I should mention these antennas were normally 2.5 degrees in azimuth and 3.5 degrees in elevation, because you wanted to come over a little mountain or under a bridge in a valley, and therefore needed the more opening in elevation than in azimuth. Next one, please. Yeah, this is a very nice thing. Already in 1996, the company of Eaton Warrett in the United States built a 24 gigahertz collision warning system, and this was built in Greyhound buses. That was serious, so that were several thousand things, several thousand units that were built. And we see here for the first time, when we go to the next slide, please, the first societal impact. You see, you don't see it right, but 100% accident reduction was possible in the Greyhound buses. They only drove something like maximum 60, 65 miles per hour that you could quite good do with a quite cheap 24 gigahertz radar. And even a rent-a-car company had a reduction by 34%. However, the whole thing had to be withdrawn from the buses again after 3 years, as the Greyhound Drivers Union forced to withdraw it. It was the first time in the United States that the drivers of the Greyhound buses were forced to show um, uh, what they do at night and so on, because the whole drive was monitored and given on CDs and places that way. And that was not the case before that moment that they got this Eden Voret CWS system. And think it over, this was 27 years ago. All right, next one, please. Next, yeah, okay. So then came this new world in 1999, automotive radar market introduction strategies. It was in the beginning increased comfort. It became increased safety and increased economics. And the third thing, when the military was not that important anymore and all the things went into the commercial area. What is funny is increased economics. That's the same thing that we have today with the electric vehicles, reduces fuel consumption and causes less pollution. Okay, that was in the old days, and now it's not to use too much energy to drive. Okay, next slide. Not to forget, in parallel to the long-range radars at 35 and later on at 76 to 70, 76 to 77 gigahertz was the development of blind spot detectors at 16 gigahertz in the beginning in 1971 by Dunlop in the USA, later on at 24 gigahertz by US Microwave Corporation as a site detection system for big American lorries, so that you couldn't drive under the lorry. You remember American lorries have their back axle normally very far back, and it's easy to drive under the lorry because there's enough room. In 2012, we had the first 24 gigahertz UWB radar for active blind spot assist. UWB gives you more resolution in space compared to a narrowband radar. So if you're on a 3-lane road, you are able to distinguish when you're in the right lane, is there somebody coming from behind in the middle lane or in the other outer lane, so that you can still go in the middle lane without being stopped by the system. By the way, I should mention, which I forgot before, how do we come to 77 to 76 to 77 gigahertz? 35 gigahertz, our radars were quite large, as you remember from the pictures before, so we wanted to be smaller. If you go on, you get smaller. If you go higher in frequency, on the other side, if you go higher in frequency, the attenuation of the atmosphere gets larger. So if you combine those two, then you have a crossover at 77 gigahertz about, and that's the reason why it was chosen to be the right frequency. In those days when we started this work, that was in, let's see, 19... 80s about, there was nothing uh, working in that area, so we decided that with the German legislation people in that area, and so it came up to the 76 to 77 gigahertz. Okay, next slide, please. To give you a little bit an overview what it was looking like in 2012, you see the Conti RS300, you see the Bosch LRR3. Those are the first biggest long-range radars, and they were the first that were produced in 5 million per year. Shortly after that time, and on the right side, you see blind spot detection, lane change assist, rear cross traffic alert, and all those possibilities that came up with radar that you have, and you have Valeo, you have Hella, and the others that are in the field. To give you a little feeling how it looked like then, the next picture. That was a comparison test on electronic braking systems done by the German ADAC, the German Drivers Club to say so, Automobile Drivers Club. And you see that it is normally Conti and Delphi, today it's Active called, and Autocruise, a Swedish company, as well as Delphi, and so on again, and Bosch. And you see that the biggies, meaning Mercedes-Benz and BMW, as well as Volvo, were the ones that first put the thing into working. I should mention here something. It is not only a sensor that comes from the tier one, but the problem is how to bring that sensor onto your platform. That means the same sensor in different cars can behave totally different. I had a Mercedes-Benz B-Class with an LR3, and I drove an Audi 2 with an LR3, and the difference is quite large. While in my Mercedes, the engineers were bold enough to leave it on even on highways, on highway crossings, while the Audi people wanted to large distance to the front and car view, so the whole thing went out of lock-in. Uh, but being an engineer, I drove a little bit, I used my feet and drove a little bit nearer to the car in front of me, then it didn't lose contact. And when it was straight again, I only had to take my feet off, and the thing was settled already and hadn't to lock in again. So you see, it's different. Due to my job at Mercedes in those days, I drove a lot of cars like Hyundai, like Kia, like BMW, like Lexus, and so on. I made a lot of benchmark drives, and so I learned all this. So let's go to the next picture. State of the art, the first brake assist. Yeah, that was the beginning. You see on the picture on the left side, a long range radar and 4 short range radars being built into a car. That was the beginning in 2014, pre-save brake. You had a signal that came up to you, so that was the first thing. Then you got approximately 1.6 seconds before impact. The brakes were pre-programmed to brake quickly, and if you still didn't work, then the braking itself came, so that nothing should happen. That was one of the beginning. You had cars like this from Toyota, from Kia, from Hyundai, and so on. That was the usual thing in those days. Okay, next slide. Now I want to switch a little bit my focus to China. China is a large country, and in the moment it's that way that a third of the production of the cars worldwide goes into China. So especially the German high performance value cars are exported to China heavily, like Mercedes, BMW, or Audi. So they wanted to come up with something by themselves. So the National Natural Science Foundation of China was founded in 1998, and they had first tests with test vehicles, and then parking age in 2010, urban tests in Inner Mongolia. Didn't really want to say that they did quite something there for tests in Inner Mongolia. By the way, the first thing was a Fiat car and then a Hyundai car. The problem is not all the old cars, they were mechanical, and you needed some car that is entirely electronic. So you had to have actuators. If you have sensors to do something with the car, you need actuators to go to the brakes, to go to acceleration, to do this, to do that. And the Chinese cars didn't have that. The Honky Q3 was the first one to have that. So in 2012, universities in China got involved, and in 13 it was already more than 118 universities involved. And then in 2015, you had the iBus, the Intelligent Bus Drive, on the 29th of August. And later on, Uway came in 2019 with full sensor development, with a full sensor development program from sensors, system on a chip to car installations. Next slide, please. I myself was in Chengdu in 2015 on that fair. So these pictures that you see on the right side, I did myself. And there's a lot of work ongoing in those days, and they had the Tucson SUV of 2012. So you see a lot was there already happening. All right, next slide. The story of the Yutong iBus. Yutong is one of the largest bus manufacturers worldwide. And they tested the whole thing. They had 4 radars, a long-range radar, 2 short-range radars, and a medium-range radar to the back. They had a LiDAR, they had 2 cameras, night vision systems, and the result was then 26 kilometers driven autonomously. There was a driver still sitting, but he didn't touch the wheel at all, with 26 traffic lights in between, 2 stops for passengers to go in and out, and several passings of sequences with other cars, and the maximum velocity the bus drove was 68 kilometers an hour. That was already in 2015, and gives you a little feeling what is happening in China and with how much energy and impulse they are working in this field. Next one, please. Yeah, that gives a little bit of a resume where we are these days, where we are really. We have about 350 million cars equipped with radar units on our streets worldwide. That's what is at the moment, which is not much when you think of 2.5 billion cars worldwide. This is quite a small amount of cars equipped with. It is estimated that about 40% of these are working in the 76 to 81 gigahertz frequency range. They are long range as well as short range radars. The whole thing is backed politically. The digitalization initiative of the European Commission is one thing. That means sustainability. I come to that later again, what we can do to use less resources than we do in the moment for things like this. I already said that combine Vision Zero with zero emission, and that way you can take the same sensor for 2 different possibilities. Then there's the Konzertierte Aktion Mobilität of the German government, making L3 legally possible. The MB class for highway pilot is the first thing that is functioning that way. And more importantly, the whole thing is backed by insurances, as the ADAS effect technological procuring, you can procure money. That's the trick. And from automatic emergency braking, you're getting over to automatic emergency steering. So, as you see in the picture on the right below, even a ball on the street, the car will maneuver off and the kid will not be driven over. So, the next slide, please. Here see what we know already since a long time. In 2008, Mercedes-Benz had done a first study over 3 years showing that when you have something like emergency braking, Distronic Plus, as the whole package was called that way, you could reduce the heavy accidents by, what is it, 28%, and the other accidents, the medium accidents also, and only the small ones, because all the larger became small ones. Even that went down by 5%, showing that this is really a possibility to reduce it. And then even more, Checham Insurance in England, they made tests in 2017 over 6 years with their own cars that were insured at their company, and you can see that they were able to save 20% of money due to being building in a radar into their golf cars. It was always the same car, and the upper part is LiDAR in a Volvo, and you can even combine that. I don't want to go into that too much. And the most important thing in both cases, the injuries for third parties was 20% reduced, and that's already something and quite interesting. Think that over. That is because we have sensors in cars, and that way we can make our life safer. Next one, please. Where we are now. This is brand new. This is from Cédric Malaquin from Yole Development in France, and he gave this talk just 4 weeks ago at the European Microwave Week in the Automotive Forum, where the highest and newest things were told and said. And you see, we are here now. L1, this is something that we have since 10 years already, feet off. I have to say that I drove at least something like 1,000,000 kilometers in my life. And I would think 200,000 kilometers I already drove without using my feet. And you can get used to using a car like this without a big problem. And now even more comes up. We have a standard radar, we have the 4D radar, we have the high performance imaging 4D radars. That is all upcoming, and you see that is over time upcoming. So, next one. In the beginning, you had one radar, one LiDAR, of one radar to the front and two at the sides, and we are getting to something like 5 radars, and it's getting more and more in that direction, that we have more sensors in different cars. You see on the right side in 22, what was it? 1.5 radars and 3 radars in 2028. So things are changing, and we will have more and more of that, and that gives more freedom. Next one, please. The technology trend, yeah. 4D imaging is what is necessary for 76 to 81 gigahertz. There's a lot of startup companies in EU as well as Israel, especially in Israel. You have Arbe, Invisense, you have Wire, and they already have developed the semiconductors and the processors that would make it possible to have something like 48 by 48 transmitters or receiver possible. And that's what they all want to have maximum freedom to really see what's ongoing and where we are going to, and what has to be taken care of. The problem of these days is something else. 48 by 48 transmitter receivers needs quite a lot of antenna setup, And these antennas as microstrip patch antennas at 76 to 81 gigahertz. This is a lot of attenuation. So on the automotive workshop in Berlin 4 weeks ago, we had the situation that if you do 24 by 24 transmitters receivers, has had less capability as a spares unit that had only 12 by 20 transmitter receivers. So due to the attenuation, the capability and the performance of your radar set, even if you could process it, goes down. And that's quite an interesting thing. We come to that in a moment. The next one, please. Here for the radar market outlook, you see that there's still a lot of growth. And we go from one radar to 5 radars to even more radars. The next one will show that even better. Next, please. Yeah, here's the entire market forecast. In 22, you have quite a large area of normal legacy radar, and only the the 4D radar is quite good, and the super imaging radar is a small amount yet, which is violet. And you see that things change. The standard radar goes down, the 4D radar up, and especially the 4D imaging radar will get a lot more in the market. And not to forget, you see this light blue, which is in-cabin radar, and I will come to that a little bit later now, but we talk about the rest before. Okay, so next slide. You see that Hyundai, Mercedes, BMW already had L3 in 23. They think that others like Volvo, Tesla, the Chinese, Kia, Hyundai, they come up in this year still, and Stellantis and Polestar, they are thought to come up something like that. So the AD timeline towards eyes off the road is quick. Eyes off the road means no hands on anymore, and that's an important part. So next slide. Here you see a little bit of the state of the art. You see on the left side Mercedes with one LiDAR, 13 ultrasonic sensors, 6 cameras, 5 radars, and on the other side BMW with one LiDAR, 12 ultrasonic sensors, 5 cameras, and 5 radars. This is in the moment the maximum of what is available and what you can get on the road. Now with that, we come to another thing. If just think it for yourself, if you have an accident, what's happening then? Until 5 years ago, the worthiness of your car was supposed to be counted without all those sensors. Now that has changed, and the price of the sensors goes in as well. Perhaps as a good example, look at my car. I'm driving now since, what is it, 10 years nearly. It is full of sensors. The normal price in those days was 18,000 euros, but I had to pay 42,000 due to all the sensors that are in the car itself. So you see, this is important, and you have to think of things like that. Okay, next one, please. Yeah. Already last year on the Automotive Forum in 22 in Milano, we talked about new antenna realizations. You see here the airfield waveguide from IMEC AT&S, an Austrian Technology and Science Center, integrated waveguide from Huber und Suner, and multi-layer waveguide from Gapwaves. You see that is waveguide again and off from the microstrip. Next slide. You see here that gap wave is a very unique structure. You can easily apply it. There's a lot of mathematics being inside, and that way you can produce it easily. In the next slide shown, you see the normal waveguide with two layers on the left side and the thin version of metal sheet plates that are just bolted together, and that's it. And that's an easy and low attenuation antenna setup if it works right. Next one. And you see that those antennas are also quite good, as you see here by the measured results on the lower part of that. So furthermore, next slide. I talked about sustainability and how to combine things, and this is one of the possibilities. You have a light bulb, and within the bulb setup, headlight setup, under the headlamp cover, you have already a Fresnel lens on the left side where the radar is coming from below and then reflected to the outside world, and you see how that works. That means integration of light and radar, and that was already done in radar glass in 2020. You see the paper being shown on the right side on the bottom. The next one step further now to integrate three different functions: LiDAR, the LED of the high beam, and the radar in the same setup. That way, you have just one unit for everything, and you don't need different radomes, you don't need different space. This is sustainable and is saving resources. Please. I said something about in-cabin monitoring, the second growing radar market. You can have cameras, LiDAR, low frequency UWB radar. From I think 24 on, you have to have something like this in cars in Italy, and then it comes in Europe as well, to monitor if there's a dog, if there are kids forgotten or something like it. And a wonderful solution to do that is using a 60 gigahertz radar with one or up to three, so that the whole inner cabin area can be seen. Next one, please. This is the integrated waveguide in radome concept from Huber and Zuna. Just some slides back, I introduced to you that waveguide is now coming up again in special printed versions and setups with metallization. And you see here, this can be used for an integrated in-cabin radar that is very easily to be built when you know how to do it. And this is the area where a lot of mathematics goes in and a lot of simulation, and that's something the young ones can do, and still a lot of things have to be done. Okay, next one, please. Yeah, this is still open. HMI standardization. When you go into a car, this is all different. The second from the right is Mercedes. The second from the left is Mercedes. Second from the right, AN. Right is Hella. Left is BMW. So there are different possibilities, and this all has to be brought together. Otherwise, the customer and the customer, the driver, doesn't use all these wonderful things because it's too complicated to make it possible. Next one. This has the ADAC as well seen. This is social acceptance. ADAS and emergency braking system, emergency steering systems, they need explanation with videos and so on. And then the Autoplan pilot really does work as an L3. And we have to think about possibilities how to bring it over to our real customer. Okay, next one. Yeah, brings me to my conclusion. We have come from 35 gigahertz impacts to sheet plate antennas at 76 to 81 gigahertz. You see the difference. The 60 centimeters about two antenna system of 1964, and now the Hyundai system of this year with sheet plates. We need faster processing. We need low loss antennas realization for 3D imaging. That's what I have explained heavily. You have the sustainable concepts like smart headlight. You will have something new coming up with in-cabin radar, which is a new area that comes up. And we have to talk about user acceptance and trust. Trust is a real thing, and HMI monetization. And I have to mention here something special. The tier ones have already demonstrated industrial vision and leadership at the European Microwave Week in 2022 in Milano. The radar interference initiative between Mobileye, Bosch, ZF from Germany, Huawei, and Qatar, uh, Chinese Aerospace Technology Research Center, something like this. I don't know the full name anymore. They work together to find out what to do and how to design radars that the radars don't interfere with each other. So one is not killing the other one, because there are 350 million on the streets and you can't make them obsolete coming out with something new. Next slide. This is, you can read it yourself, but the important part is the thing at the bottom. We have not reached nor even approached the limits of achievable radar performance today. That was said by the boss of BAE Systems in England, Les Gregory. That tells us we have still a lot to do, we have still a lot to think about, and that's your job, that you can come up in here now and look for the part that you like to work on. Next slide, please. Acknowledgement has to be done. Next one, please, which I think is the last one. Yep. Thank you for your attention. It was a quick jumping over all the new things, and you see, radar is it, and we all knew that since a long time. As you see, the Stone Age is shown in this comic. Okay, that was it, and now I'm open for discussion, for your questions, if you have some of those. All right, Emmanuel. Oh, I don't hear you.
Okay, the technology and me. Thank you, Holger. Very interesting the subject about this technology. Um, I believe that maybe another problem will be the user, the people accept this technology,
Yeah.
and
The
and
societal
the
aspect, you really
society.
have to bring it over. Uh, I know that I can be trusting the system. I drove through the European Alps with a new sensor, and on a road at noontime, so there was no shades for the camera and so on. And it was new asphalt, new lines on top, and I was driving through the mountains, only doing every 20 seconds touching the steering wheel, and everything was done by the machine. I had a wonderful mountain area to look at,
Mhm.
and the car accelerated due to GSM. It broke down in velocity due to GSM and drove through the small curves, only the 180-degree curves I had to steer. So that was a wonderful experience, but you have to be trusting the systems.
Yeah, because it's similar to we have friends that are they are physiotherapists. You know, the people that make some knowledge about the body,
Yeah.
and but the people of the society don't understand the importance that you need to attend your body with this kind of people of experts,
Mhm.
and it's similar to this case, to this technology, because you know that you can trust in this technology,
Yeah.
but you, because you are the expert, but there are other people, and maybe we need to uh, generate a new project to make this culture or this education about this technology. So there is a new
I think
challenge.
that would be a good idea, cultural wise, to talk about it
Yeah,
and bring it over that the people can be able to accept the situation and to
yeah,
make it
right.
happen. Yeah.
Okay, Holger, we have here some questions from the audience.
Okay.
Um, the first one is, does the increase in sensor speed from 24 gigahertz to 27 gigahertz and more have to do with how quickly the sensor detects change in the input, or why this increase in gigahertz, uh, which is the impact of, or what is the benefit?
He wants to know why we went higher in frequency from 24, 35 gigahertz to 76.
Yeah,
Easy. You don't have the space in the front of the car. A big 35 gigahertz antenna is like the frequency three times larger than at 76 gigahertz, and that's the only reason. You have to fit in the front of a car, and then don't forget you have wonderful designers in those OEM companies that there comes no sensor anywhere. You have to go this or that way.
okay, okay, great. We have here another one. What are the differences between automotive millimeter wave radars and continuous frequency modulated radars? When is one or the other used?
Okay, continuous waves means you want to have the Doppler only. With that, you can see movement, but you can't measure distances. Frequency modulated continuous wave is taken, you go up and down, and that way you know where you are and you can measure distance. And you also can do something else. You can use pulse code modulation on a radar like that, but that doesn't fit together nicely with FMCW. It's better to have FMCW with different steepnesses in going up and down and how to make the frequency change and so on. There's a lot of possibilities, and the signal processing guys, they totally know what to do. When you go to MIMO systems, the 48 by 48 transmitter receiver systems, you use digital beam sharpening. You take the Doppler information to make things true or not true by the signals that get in and so on.
Great. Okay. Thank you, Holger. We have more questions, but I will, by the, because
Yeah,
we have
just go on.
we have not much time, but I will ask one more.
Okay.
Uh, how, let me select one of it. Okay. How are concerns about electromagnetic interference between different radar systems in a modern vehicle being addressed?
Yeah, okay. That's what I said already, that the tier ones have founded this interference um, working group between ZF, Bosch, Conti, and so on, and the Chinese, just to think about what can be done, how to modulate, so that you have modulation possibilities that don't disturb and interfere with the other radars around you.
Great.
You always can do something, and if you know what the others do, you know, um, you need something like 150 megahertz in the band that's allowed. You have nearly a gigahertz of band at 76 to 77 gigahertz for long range radar. You only need 150 megahertz, but you have something like, say, 800, 900. So if there's a lot of traffic, other radars going around, then your processor says jump to one of the right or the left side of the band and see if there is not that much traffic, and that way you are rid from the interference that you might have in the middle where a lot of things happening.
Okay.
This is the version like we do it since 10 years, like the cars that are on the road already.
Yes, very interesting how, as you say, we know that the answer is the radar systems a lot of
And
years ago.
yeah,
Uh,
in the beginning, it was a radar system with just one antenna. Now
mhm.
we had a digital beamforming. We have MIMO. We can look at the same time to two different directions. We can go off that way from interference and so on. And we can switch the frequency. It was a fixed frequency in the
Yeah,
beginning, and. So it develops further and further and further and gives more possibilities, and that way makes the whole thing safer. And you see, I'm going over the Brenner to Italy, and I set my radar up at the Brenner behind an Italian car. In Italy, the fines are very, very expensive. So nobody is driving too fast. Take a fast car and just stay behind. And for the next 1 hour, you don't need to use your pedals because the car in front of you brakes when there's less velocity, if there's a limit, and it starts again afterwards. I just have a chance to learn Italian from my city because I'm not totally um, on alert of driving.
right.
Those are
Okay.
the possibilities. You only have to trust the system.
Yeah, and maybe this will be a very big issue because we are talking about the people, the how they think, and so it's not technology. It's
Yeah,
people, are humans. So okay, Holger, thank you very much. I know that your information and all your knowledge will be helpful for all our students and professors. And only to say thank you.
if there are further questions, you have my email. You can forward the
Great,
questions of the students, of the people to me, and I will do my best to answer them. Okay,
great. Thank you, Holger.
thank you.
Buen día,
Bye bye.
gracias.
De nada. As you say.
Muy bien, gracias a todos los que nos siguieron en línea. Gracias por su participación en este Congreso Internacional de Investigación de VM. Hasta pronto. Thank you.
Thank you.
Una producción de VM Radio.